Hello, everybody. All right. Now we're going to start taking some of the things we've been learning lately, and we're going to start putting them together into a bigger picture. We've been talking about individual stars and how they're born, how they live, how they die, what happens after they die. We've talked about binary stars and how some stars are born so close to each other that they're trapped orbiting around each other. What if you have a cluster of hundreds of stars, or thousands, or a million stars? These things really exist out there in the galaxy, and in lots of other galaxies too. On the face of it, a star cluster is exactly what it sounds like. It is a cluster of stars all together. But why? Well, we've said why, right? Why do stars live in these clusters? Because they were born in those clusters. Stars are never born one at a time. Stars are born in their molecular clouds, in their stellar nurseries, hundreds, thousands, hundreds of thousands of stars at a time. And so when you look out in the sky and when you see a cluster of stars, you look at that and go, aha, those stars were all born together. They are all the same age because they were all born at basically the same time. And because these stars are all close to each other, they're all basically the same distance from us. And that's something really special. Because if you just pick out any random stars in the sky, you can't look at a star and know whether it's near or far just by looking at it, right? You've got to do something like measure the parallax to figure that out. Do you know whether the star is young or old? That's also really hard to pick out, right? Stars on the main sequence, stars spend most of their lives on the main sequence, right? And stars on the main sequence don't change very much. The sun today looks basically the same as it did when it was 1 billion years old, and it's going to look the same as it does today when it's 9 billion years old. So is our sun 1 billion or 5 billion or 9 billion years old? Well, we know that the sun is about 4.5 billion years old, not actually by studying the sun, it's by studying geology, by studying rocks. So just looking at a star and knowing whether it's young or old is not trivially easy. But when you're looking at a cluster of stars and you say, aha, those stars are all together because they were all born together, all of those stars are the same distance from us, they're the same age as each other, they're the same metallicity, you're getting rid of so many variables, and that lets us figure out things that we can't figure out just from any random star. So that's what we're going to unpack right now. What are some of the things that you can learn from star clusters that individual stars can't tell us as easily? Like I said, one thing is distance, right? Like we've said before, if you can watch a star and measure its parallax, hey, great, you're good to go. You know what its distance is. But most of the stars in the galaxy, and therefore most of the star clusters in the galaxy, are too far away. They're too far away to measure their parallax. So what do? Well, you got to pick another tool out of your toolkit. Main sequence fitting, this is the name for it, is another tool in our toolkit. Because if you look at the absolute magnitude versus temperature, this is basically an HR diagram. Absolute magnitude is another way of talking about the luminosity of a star. So this is a graph of luminosity versus temperature. This is an HR diagram. The red line here, that's the main sequence for all main sequence stars, given the luminosity and the temperature. So if you look at a cluster of stars, and I don't know what its distance is yet, and therefore I don't know what its luminosity is yet. So you take a bunch of stars in this cluster, and you measure their apparent magnitude, or their apparent brightness. In other words, you're measuring flux. And if you graph the flux of these stars versus their temperature, you say, well, these stars line up like this. Well, this must be the main sequence. That sure looks like a main sequence to me. But, why is the main sequence down here? Why do these stars look fainter than their luminosities would say they should be? Well, if the stars look fainter, it must be because they're farther away. Because all of the stars are farther away. The entire cluster is farther away. And so this is really a slick trick where you can say, if I knew what the luminosities were, then the whole main sequence would be up here with the red line. The stars look fainter because they're farther away. How far away? Well, the fainter the cluster looks, the farther away it must be. So by comparing the flux to the luminosity, by taking the flux of the main sequence and comparing it to the luminosity of the main sequence, you can figure out what the distance is. Now you know the distance to the entire cluster. And if you know the distance to the entire cluster, you know the distance to every star in the cluster. And now you know the distance to hundreds of stars, thousands of stars at a time. Just by comparing these two graphs, luminosity and flux, you now have figured out the distance to thousands of stars at a time. It's a really easy and really powerful tool. And it's especially useful because parallax only gets us part of the way into the galaxy. And if you can see the stars in a cluster in another galaxy, then this is really powerful because now you can figure out the distances to whole other galaxies. But that's a story for another day. All right. So to recap what I've just been saying, because these stars are all the same distance from us, why would a star look brighter? Because it's higher luminosity. Why would a star look fainter? Because it's lower luminosity. But the temperature is the same, right? If you've got two main sequence stars that are the same temperature, they must be the same luminosity. The only reason why this star looks fainter is because it's farther away. How much fainter is it? That tells you the distance. And now you got the distance to the whole cluster. All right. What about the age? How can we figure out the ages of these stars? Well, let's go back and look at one of these stellar nurseries. Let's look at the Carina Nebula here, right? Remember, the Carina Nebula has main sequence stars in it, right? These stars over here are main sequence stars. These stars here are main sequence stars, right? There are stars that are already living their lives. But remember, there's a bunch of blobs of gas that are still in the process of collapsing, right? There are still a bunch of protostars that are not main sequence stars yet. So how old is this cluster? Well, we can figure out how fast stars form and how long stars live their lives to figure out the ages of these clusters. What does that look like? How can we do that? Well, let's do what we've been doing a lot lately. Let's make an HR diagram. Let's look at a bunch of these stars in the cluster, measure their luminosity, or figure out their luminosity, which we can do now because we know what the distance is, right? Now that we know the distance to this cluster, we can look at each of these stars and figure out what its luminosity is. And we can look at the temperature, right? And say, okay. And then we can also zoom in on some of these protostars. And, they're not main sequence stars yet, but we can still get the luminosity and the temperature. Let's plot them on the HR diagram too. What does that look like? Well, it'll look something like this, right? Because when stars are born, remember the high mass stars, they're the ones that are born first, and then the medium mass stars are born, and then, here's a bunch of low mass stars that aren't actually stars yet. They're still protostars. They're still evolving their way onto the main sequence. So we could call this the zero age main sequence. We're going to call this time zero. This cluster just formed, and the high mass stars are main sequence stars already, and the low mass stars are still working their way toward getting to be main sequence stars. All right. So at the beginning of time, not the beginning of time, but at the beginning of the life of this cluster, here's what the HR diagram for the stars in this cluster will look like. All right. Now, if we move time forward a little bit, okay, after a few million years, ooh, well, those high mass stars, those O-type stars, they only live for a few million years, which means these O-type stars, they've burned through their entire lives already. Right? They're now evolving off the main sequence and working their way toward becoming supergiants. Meanwhile, these low mass stars, well, okay, they're still working their way toward becoming main sequence stars. All right. If we move time forward a little bit more, okay, now finally all the main sequence stars that will be born have been born, right? All of these main sequence stars are there, but oops, these highest mass stars, they're already dead. Or at least they're in the process of dying. They're supergiants, and they're soon to be supernova and neutron stars and black holes, right? So when you look at a cluster that's a certain age, in this case 10 to the 8 years, what happens? What happens is all the low mass stars are still main sequence stars, because remember, low mass main sequence stars live longer. The medium mass main sequence stars, they're still main sequence stars. At some point, you get to the highest point on the main sequence, and then there's no more main sequence stars because those higher mass main sequence stars, they're already dead. Or at least they've evolved off the main sequence and will be dead soon. All right? This is what you call the main sequence turnoff point. This main sequence turnoff point is the highest mass main sequence star that's still around. All the main sequence stars that are even higher mass, they're already dead. The low mass main sequence stars, they're still low mass, right? But if we look at this, right, as the cluster gets older, now we've moved it to 10 to the 9 years. Right? Now the cluster is 1 billion years old. I'm going to go back for 1 second here, right? When the cluster was 10 to the 8 years old, the main sequence turnoff point was right there. Now notice what happens, right? After 1 billion years, the main sequence turnoff point has moved down the main sequence because the stars that live shorter lifetimes, they're dead already. This right here, this turnoff point, this is the highest mass main sequence star that's still around. This star is just about to reach the end of its lifetime, right? This is about to die. That star right there is about to die. And so if we can look at that star right there at the turnoff point and say, well, if that star is about to die, then its age is equal to its lifetime, right? Because it has lived for the entire length of its lifetime and it's just about to die right now, right? So, but remember, all of these stars were born at the same time. All of these stars are the same age, which means if we can look at that main sequence turnoff point, and if we can say, well, if this star's age equals its lifetime, all we got to do is figure out the main sequence lifetime of this star, and the main sequence lifetime of that star is equal to its age, which must therefore be the age of all the stars in the cluster. And now we know everything. Now we know the age of the entire cluster. So this is a really powerful tool. Like I said, stars don't change very much over their main sequence lifetimes. They're sitting there pretty much. Until a star evolves off the main sequence, and then it starts evolving and changing rapidly. But that can take millions of years, and that would take a lot of time to see that happen. There's a much faster and easier way to figure out the age of a star, and that's if it's in a cluster. All right, let's look at an example here. Okay, let's evolve this cluster a little older. All right, now notice as the cluster gets older, the main sequence turnoff point moves down the main sequence even more. So let's say you look at this cluster. You measure each star's luminosity and temperature, you plot the HR diagram, and you go, aha, right there, that's my main sequence turn-off. You're catching this star in the act. This star is just about to leave the main sequence. All right, what's its luminosity? Well, okay, that star's luminosity is about 65 solar luminosities. All right, well, the luminosity of a main sequence star only depends on mass. So if you have the mass of a star is luminosity to the 1 over 3.5 power. So if that star has 65 solar luminosities, then that star must have about 3.3 solar masses. Okay, so that star right there has 3.3 solar masses. Well, how long does a 3.3 solar mass star live? Well, the lifetime of a main sequence star is 10 to the 10 years times the mass to the negative 2.5 power. And so if you do the math there, plug in 3.3 solar masses, and that star has a lifetime of 5 times 10 to the 9 years. Or what is that? That's 5 billion years. So you're like, okay, that star will live for 5 billion years. But wait, it's dying right now, which means that star has reached the end of its lifetime. That star is 5 billion years old. And since all of these stars were born at the same time, that means all of the stars are 5 billion years old. Now you know everything, right? Each star in that cluster, just by looking at the stars and plotting their HR diagram, you now know how old each star is, all of them, right? This is much more powerful. This is a really powerful tool for figuring out how old stars are and how stars evolve, right? By the time you get to a pretty old cluster, right? Let's say you have a cluster that is 10 billion years old, right? All the high mass stars, dead. They went supernova a long time ago. All the intermediate mass stars, they're not main sequence stars anymore. They're red giants or horizontal branch stars or white dwarfs. All the low mass stars, well, low mass stars live the longest, so they're still main sequence stars, slowly burning through their hydrogen. Right? This is what an older cluster looks like. All the blue stars, dead. Well, except for the hot white dwarfs, and they're not very high luminosity. The only stars that are left are, yellow and orange and red ones. Look at any star cluster. Plot its HR diagram, go, aha, there's the turnoff point. The mass of that star at the turnoff point will tell you its lifetime, tells you the age of all the stars. You can look at hundreds, thousands of stars at a time, as long as they're all in one cluster so that you know they're all the same age. You can figure out the ages of the whole cluster and therefore all the stars in the cluster. Right? It sure beats having to look at a star and wait for something interesting to happen, which, could take millions or billions of years. Rather than looking at 1 or 2 or 10 stars and watching them for millions of years hoping something interesting happens in order to figure out their age, you could just look at a cluster of stars for one night and figure out how old they are. This is why I say this is a really powerful tool for figuring out the ages of stars and how they're born from protostars onto the main sequence, how they evolve from the main sequence to supergiants or red giants or white dwarfs or neutron stars or black holes, and then what happens after that, right? All of the things we've been talking about for the last several lectures about how stars are born, how they live, how they die, what happens after they die, a lot of those discoveries happen from looking at stars in clusters, because you're looking at high mass, medium mass, low mass stars all together, all the same age, all at the same time. And that means you can make discoveries a lot faster and easier than if you were looking at just random stars picked out of the sky. All right? So from here, we're gonna zoom out even more and start looking around the whole galaxy. And how do we look around the whole galaxy? Well, we're taking everything we know so far. Take what we know about stars, take what we know about the interstellar medium, take what we know about clusters of stars, and then let's use these tools to go one notch farther, looking into the deep recesses of the Milky Way galaxy. All right. I'll leave that there, and then the next lecture we'll pick it up from here. All right. Have a good one, everybody.